Hey guys, so last time I gave a really big overview of what was happening with my pathfinding algorithm. Now I'm going to go a really deep dive into how Dijkstra's algorithm works. If you remember, we have a graph. A graph is made up of vertices, or nodes as I like to call them sometimes. There are edges between each node, and each node has an adjacency vertex or matrix that shows you the weight between each adjacency. Now I didn't go over weight last time, but what weight means is it's like, it can be really anything, but for my purposes, it's going to be how hard is it to get from 1 to 2. So to get from 1 to 2, it will cost 2 weight. And basically what we want to trace is we want to trace the path of least resistance. So whichever one has the least weight in it. So to do that, we're going to use Djkstras. So for this example, are going to start at node number 1 and end at node number 2. Now before you calculate everything, what we need to do is we need to make 3 parallel arrays. Now what these arrays mean, what parallel means, is that the first node corresponds to this node, which corresponds to this. So, and then the second one corresponds to this second one, and so on and so forth. So what it means is whenever we change something in the first one, it will affect the first one in the other arrays. So first, the distance array. It's a really simple array. That's the distance from this node, because that's our start, to either itself, node number 2 over here, node number 3 over here, and so on and so forth. Okay, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it goes down the right and then it wraps around. So the Boolean array tells us whether we have checked this node. And that's just for our algorithm to ignore it if we've already checked it. Because the cool thing about Djkstras is it will only check each node once, and that's it. That's all we need to check. The third one is a previous path array, and this is made up of a ton of other arrays. So you have arrays within arrays, and this is going to be super helpful. It's going to tell us the path from the first node to itself, which will be empty, the path from the first node to the second node, which will just be like 2, and so on and so forth. I'll fill it in because this example is super simple, and so it may be very obvious what the best path is, but I'm still going to go in step by step to show you how the algorithm works, because when you expand it to a much bigger graph, then it gets a little more complicated, and this algorithm will just do it for you, and you don't have to go through all those steps. So after we initialize all these arrays, we put infinity or max int, or you could even put just a really high number, depending on what you want to do. In for each of these, we fill up this Boolean array with false, and we fill up this previous array with lists, empty lists, or empty arrays. Sorry, I might use lists and arrays interchangeably because I use lists all the time in C#. So, and then we want to start at the first array. So what we're going to do is we know that this distance is going to be 0, because if you want to get to itself, it will take 0 weight because you're already there. And now what we're going to do is, I have a little cheat sheet over on the right because I always forget, is we set this to true, because we go, hey, we are checking this first one. Now we're going to look at the adjacency matrix. So what we're going to do is it's 0 to 0, or infinity, 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 infinity. Oh, no, that's, whoops. I'm not going to lie, I'm going to make a couple of those mistakes. I hope I can catch it. Infinity. Okay? Oh, one more infinity. So now what we do is we compare this spot to this spot in the distance array. So we go 2 plus 0 is less than infinity. Okay, looks good. So then we erase this and replace it with 2. Because remember, we want to find the path of least resistance. So we're looking at 2 plus 0 is less than infinity. And this 0 comes from here. I'm going to use a different color. It comes from here. Because remember, we still want to add the previous distances. Now this may make more sense as we go on and we see more of these. So that's 0. And then we check the next one. 1 plus 0 is less than infinity, because we're checking this node. All these infinities are not less than infinity. I mean, you could make arguments that some infinities are less than other, but we're not going to cover that at all. So this is 1. Okay, perfect. Then we add it to the path. I actually already did that. So we add 2 to the path, and then what we're going to do is we're going to add 6 to this path, because 6 is the node number. Because remember, we're looking at this. 6 is essentially the index where we will find that location. Because this is index 6, assuming we start at 1. I'm going to assume we start at 1. We go 1, 2, 3, 4, 5, 6. So it's at 6, and that's the path we're going to take. Sort of makes sense? Okay, so now what we're going to do is we are going to find another one. So we've done that. We've added the path. Now we find the vertex with the minimum distance, which is this one. So we're going to check out 6. See? 6. And first step, set the Boolean to true. Perfect. And then we go through and we go, this Boolean, let's find the adjacency matrix. So we've got 1, infinity. So the infinity is there because there is no path from 6 directly to 7. And all we care about is the immediacy, is the immediate path. So we got this, this, this. Alright, so now let's see. 1 plus 0 is not less than 1. So we don't do that one. Then we go 1 plus 5 is less than infinity. Now this is actually, there's also a 0 there. So this is 0 plus 1, plus, actually no, there's no 0 there. Ignore that. Take that out. Because we're only adding the previous one. Because we technically don't know what the ones before it were in this instance. So we go, okay, that's less than infinity, so we put 6 there. And that's the only change we make. Oh, we'll put in 6 and 7. Because we are adding the previous path and then putting 7 on top of it. Adding the current node on top of it. Alright, and then we keep going. I'm going to run through a couple more examples in depth, and then I'm just going to try and speed through them. So now, these are true, so we ignore that these are technically the smallest, and we go to 2. So let's run this through. We go, yep, that's true, and we set the Boolean to 2, and now we check the adjacency matrix. This is 2, 0, 10, blah, 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 infinity, infinity, and then this is 0, 0, it's infinity. What is this? 3, infinity, infinity, infinity. Okay, so now let's check these. 2 plus 0 is it's greater than 0, so we don't do this. We don't do this one. 10 plus what is it? 2. It's greater. That's less than infinity. Okay, looks good. So we'll replace this with 2, 12. And then we'll do this path, which is 2, 3. Sorry, the path is just going to look ugly. I couldn't figure out a good way to do it. And now we do, okay, so what about 2 plus 3? Is that less than the 6 that we currently have right there? And we go, yes. Okay, so then we replace this with 5, because 2 plus 3 is 5. And then we need to change this path. So this path will now add this previous path, so that's just 2, and then it will go 7. Wow! That's pretty cool. I actually find that super cool. Perfect. So now we're done with this, and we found the shortest path to the 7 one. It's not 6, 7. It's actually you go 2, 7. Sort of makes sense, hopefully. So now I'm going to speed through these. We're going to do this. That's true. True, and what is this? 6 plus 5 is 11. And then what is this? 3 plus 5 is 8. That's a 3. 3 plus 5 is 8, which is greater than 2, so we don't swap that one out. Move on to the next one. This is 11. I did that wrong. Okay, the next one we check 11 because it's the lowest and it doesn't have the true. So 11 is here, so that's 18. And this is 11 plus 4 is 15, which is less than 12 or greater than 12. God, I'm going to make so many mistakes here. Greater than 12. So we don't replace this one, but we do replace this one. And we put in the path as well. The path to this one is what? 2, 7, 8. Yeah, just don't look at the numbers. Just listen to what I say. Okay, perfect. And then we just keep rolling down. So what I'm going to do is I'm going to skip all these. I'm just going to say true, 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 and get to this one, which this one should be 12 plus 2 is 14. 14. This one is 24. That one's 18, and this one is 19. So now we're going to do the final two a little more in depth again. So the final two, remember, we ignore these first four, and then the first four, so these ones, well, these ones, because of this, these are all true, so we ignore them, and we just grab 19, so that's node number 10. Node number 10, we set to true, true. God, I am losing it, guys. We set that to true, and now we go, okay, adjacency matrix, infinity, 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 INF. I'm just going to do that. INF. Then this is 3. Then this is INF, 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 and this is 1, and then 0. So now obviously 19 plus 1 is less than 18, but once again 19 plus 3 is less than 24. So once again, see, we found this 24, this 24. So we found a faster path. So then all we need to do is we need to look right here and we go, okay, so this previous path was 2, 7, 8, 9. And then we add 10, and then we add 5. And that's the path. So if we want to go from this first node to the 5th node, this is the path we would take. We would go 2, 7, 8, 9, 10. And then right to 5. So the reason we have this previous path array is specifically so that I can automatically go, so if I'm here and I want to go here, how fast is that? And it will go, hey, this is the path you want to take. And then the distance array will tell me, and it'll take you 14 to get there. And that is super helpful for calculating what we want. Now I'm going to show you a quick example. Well, hopefully it's quick. I might over-explain it a bit. But here's the quick example, blah, blah, blah. These animations that I added are going to take a long time. So we've got Moskowitz, Mr. Big, Longbeard. So I'm going to show you something that will be pretty interesting. So we're going to start and then immediately pause. So right now, oh, I got to change it to windowed real quick. Okay, let me grab up this, my writing. Actually, let me go back quick. So you remember how I said you have a node, and then you have an edge connecting the nodes? That's a bit of a lie, because what you actually have is you have a double one-directional node. So if you're going from 1 to 2, then that allows these edges to have different weights. So let's say this is a weight 2 and this is a weight 3. This is super important to have, for me to have a double-edged node. Not everything needs one directional edges. And the reason I do that is because if you are in a node and you are trying to leave it, then when you cannot go into this. The node is set to 0. Whenever you go into a node, it's set to 0 because you don't want anyone else coming into the node. So you set the weight to 0, and then our Djkstras algorithm will go, oh, it's 0? Well, that means we can't go into there because we can't go into there. And so then, sorry guys, I'm getting lost. So it's double directional, so then we can go, okay, you can move out of there, but you cannot move into this node, because let's say we've got a fighter here. You can move out of it, but you cannot move into that. I hope that that makes sense, because now I'm going to keep going. So right now, this fighter is looking to go like here, you know. Remember, they're looking for the adjacent spots they can go. And so they go, okay, that's all good. I can move just like right here, and that's good. Now this fighter, because someone is already in this location, they cannot move there. They cannot go, okay, I'll just move to the right. Because right now, that adjacency vertex is set to 0. So they're like, okay, I can't go there. So what you'll actually see when I hit play is that this fighter will, I believe, move up there. He might actually do this little thing, and he might move up and down, because as soon as this guy moves, there's going to be an open spot for them to go through. So let's see. Yeah, oh, he did it. He did the little up and down, because as soon as that guy moved, they calculated it again, and they're like, oh, I can actually get in there. So that's the basics of how Djkstras algorithm works. I mean, there's more validation I do because I want my grid-based thing to be a little more complex. I want to add a little more abilities, a little more stuff like that. But that's the basics. I hope that this helped out. And if it didn't, I'm sorry. And if it made it more confusing, I am really sorry. But, you know, comment what helped, like and subscribe, join the Discord, do whatever you want. See you guys.